Okay, so to start with, I would like to thank the organizers. And so my role here is that of presenting the activity that we are doing at the University of Leiden in my group, which is in the Department of Physics. So I'm a physicist like a few other people around, including Stefano and many other eminent scientists here, which means I can refrain from self-defining myself as a neoclassical economist or an orthodox one. And I will start by presenting an overview of problems that we deal with. So let me just start, and these problems are all around systemic risk and how we can estimate it through networks, but in the particular case where the information about the network is not completely available. So I will start with concrete examples, and then I hope that some take-home messages will build up during the course of the presentation. So, well, we all know that interbank networks are affected, so the data about interbank networks is affected by the problem of confidentiality. Okay, so we know that these networks, as Stefano brilliantly exposed so far, they are crucial. So understanding this structure, having access to the structure and the detailed structure of these networks is crucial for the assessment of systemic risk or for running different shock scenarios and related policy scenarios that can counteract this. But the problem is that what is public is typically each bank's total exposure towards the aggregate of all other banks. So we know about total assets and total liabilities of banks, but we don't know who is connected to whom. At least surely not from public data, but in many cases not even central banks know this about their own banks. So there are techniques that have been developed to reconstruct interbank networks from partial information. And this image that I've put here is actually, I think, one of the first studies of interbank networks. This is a network of Austrian banks. This study was done by the group of Stefan Tarner in Vienna, which is represented here by one of the next speakers. And actually, this is a reconstructed network. So they started like everyone has to, from total assets and total liabilities, and there are algorithms that have been implemented to reconstruct, to infer the probability of linkages, but typically these probabilities are unit probabilities for a reason that I will show in the following. So what these methods typically do is to find weights, so volume of exposure among pairs of banks that are consistent with the known margins. So that for each bank you reconstruct correct, so the total assets and total liabilities will be the empirical ones. But what these methods typically are not able in doing is to have access on the topology of the network. And we now know that, I mean, this problem of systemic risk is strongly reliant on the details of the topology. So basically we can frame the problem in general in this way. So we have to imagine that we have only access to bank-specific information, like in this picture on the left, where you have banks about which you know only local information. And from this local information, you have to reconstruct a network that is consistent with it. In this case, you see that if the local information is how many other banks each bank is interacting with, then the problem is matching all these half links in a way that that a consistent network is created. But of course, there are many, many ways you can do this. So if you want a least biased way of doing this. So how do you select among the possible options? Well, we know from physics and from information theory that the maximum entropy method is a rigorous way for doing this, so that you are using only the information that you know from the data, you maximize the entropy of your collection of possible networks that are consistent with this data, and then you know that for granted this will give you the least bias, okay? So that you're not biasing your inference arbitrarily, okay? You're making only use of the available data. Okay, so we want to do this in a way that privacy is still protected, so we will have connections probabilities at the end. But we want higher order effects to be predicted quite reliably, okay? So, and this is an illustration of what the traditional approach does. So the traditional approach is basically the one where for each bank you only constrain, so when you maximize your entropy, okay, then you say, okay, about each bank I know only assets and liabilities, and then the result of this is that you will create a network which is completely connected, basically, and the weights of the network will be such that the margins are correctly reproduced. But this creates a completely homogeneous network. And it has been shown that when you do like this, if you run some scenario analysis on this network, or if you measure systemic risk, then the result is that you severely underestimate the effect of defaults. Okay, so and a way where you can realize the poorness, say, of this method is in this plot where you are looking at the average exposure of neighboring banks of each bank. So now you see that there are many points. So different colors represent different networks, and each point in a cloud of points of the same color is a different node, so a different bank in the same network. So you see that the true hidden value is very badly reproduced by the method. So if for every bank I want to guess what is the average exposure of the neighboring banks that that bank has in its own network, then you see that the method gives flat curves, which means that for the same network you get the same value for every bank, precisely because at the topological level the network is completely connected. So every bank has basically the same set of neighbors, which is the rest of the system. Okay. What we noticed is that if you have additional information about the topology instead, which from a network point of view means introducing the knowledge about the degrees of the bank, so just the number of connections that every bank has, then the agreement is improves tremendously. So the message here is that it would be highly desirable that among the accessible information about banks, one knew also the number of partners. Just the number of trading partners, I mean, okay? So it's like asking whether you are married or not without asking the name of your wife or husband. So it's something that is not so unimaginable, but still, I mean, this is something that is non-trivial. So then what we are doing next is trying to relax these conditions. So well, can we do equally better or maybe slightly worse, just only slightly worse by knowing much less about the system. And this is just a parenthesis. So the same problem, if you think about it, is encountered in other fields in economics, like in trade economics, where basically if you have a network of countries that trade different goods, there is the prevailing gravity model, which is still the most standard tool analyzed to model international trade flows, but the drawback of the model is that it produces a completely connected world where every pair of countries, since they have positive GDPs and known infinite distances, will be connected by the model. And this is the kind, so, and then if you measure something on this network, you would see that the real data are the red points here, and the blue line is the trivial expectation by the gravity model. But if you enhance the gravity model with this topological information, then again you get this incredibly better prediction. So this is just a parenthesis for saying that the rationale behind this idea of including topological information does not only limit to the study of interbank networks, but it applies to more general economic networks. So here is what we are trying to do. So this plot is very confusing, I would say, but the final message is that if we imagine that we do not have access to the number of neighbors of every bank in an interbank network, but just the overall number of links, then there is a quite sophisticated thing you may do that allows you to reach the same level of agreement that you have if you have access to bank-specific connectivities. Okay, so this again makes use of a maximum entropy approach, but it also requires a preliminary estimation of the degrees of every bank, so the number of connections, given only the information about the total density, the average density, and their assets and liabilities. Okay, so there is an intermediate step you have to make, which makes it now much more feasible if you think that, say, regulators may now explore scenarios where you have just one free parameter, which is this overall connectivity of the interbank system, and conditionally on your scenario for this overall connectivity, you can make very refined predictions about the network. And then one step forward is once you have these networks reconstructed somehow, you want to run algorithms, including the depth rank algorithm, which is something that the group of Stefano proposed, where then you add the dynamics basically on the reconstructed network. And these plots here are just to show that both on the international network of trade, just to keep the same example as before, and on the EMID interbank network, the results look very promising. So the blue curves would be the reconstructed data, while the red ones are the one that you can measure on the real network. So you see that both the percolation measures, path length, distributions, and the depth rank analysis are very are extremely well replicated. Okay, and then there is a final puzzle that I want to, with which I want to conclude. So does it always work? And this is now a work done jointly with the Dutch National Bank, in particular with Iman, which is the next speaker. And so does it always work? So what we did in this analysis was using this idea of maximum entropy methods. So we reconstructed the topology of the Dutch interbank network between 1998 and 2008. And then we compared a few topological properties that we measured on the real network with the same properties on the reconstructed network. So basically here you see on the x-axis there is time. This is quarterly data. And on the y-axis, there are three different, very simple topological properties. It's just the number of pairs of banks which are connected both ways during that quarter, the number of pairs of banks that are connected one way only, and the number of banks that are not connected. And then the x-axis is just the z-score between the real observation and the reconstructed model, okay, and the one reconstructed by the model. So basically we are seeing on the x-axis, on the y-axis, how many standard deviations away the model is, so the reconstructed network is away from the real data. And you see that basically there is a roughly stationary regime for 10 years before the crisis. And at the moment of the crisis, there is this sudden drop or rise of these quantities. Okay? But here, what I haven't said is that the reconstructed network is not making use of the full information, so of the number of connections of every bank, but just of the total number of links. Okay? So what this plot is saying is that, okay, we record the crisis as it occurs, but there is no early warning indicator. So on one hand, it says that, okay, the crisis is, these data are affected by the crisis, which is, say, the preliminary requirement you would like to have if you're looking for an early warning signal. So first of all, the crisis has impacted this system. But if you use this reconstructed scenario, just using the total number of links, you see it coming only when it's already coming. But if you now use the number of links of every bank to reconstruct your system, this is the modified result that you have. So now the measured quantities are the same as in the previous case. What we changed was only the expected values of those properties, because we changed the input information in the model. So the reconstructed network is different than in the previous case, but the real network is the same, so the measured quantities are the same. So in the Z scores, only the expected values are different, and the standard deviations, of course. So now what we observed is that, okay, there is still some initial roughly stationary trend. There is still a very different quantitative abundance of these properties at the year of the crisis, but in between, so from the beginning of 2005 until the end of 2007, there is this intermediate regime which really looks like a pre-crisis phase that was not observable beforehand. Now, we don't claim that this is, so there is no general theory, okay, behind this. So we cannot claim that this is, say, something that would happen regularly for all crises, and we have already heard that all crises are different. But at least this is telling us that if we had that bit of information, so if we had a tool to make use of the information available about the connectivities of all banks, we might have noticed something different going on in that intermediate regime. And this is just making use of the data that are already there. So it's not invoking behavioral models or whatever. It's non-parametric. It's just making better use of the data. Yeah, so the take-home message is heterogeneity matters, and we are talking about complexity. So I think heterogeneity in this case matters because if you control for the local heterogeneity of banks and the fact that they have very different numbers of connections, you get a very different result. And what looks abrupt, if you ignore this, might turn out to be actually gradual and continuous when you take this into account. So my final message is that, okay, network reconstruction is significantly enhanced by fixing both the degrees and the strengths of banks. Far from critical events, it appears that these maximum entropy methods are very efficient, because we have seen that before the crisis, the reconstructed network had a very low Z score. But as crisis approaches, we have observed a gradual departure from the reconstructed network. Okay, so this means that if you only base your systemic risk estimation on the reconstructed network as crisis approaches, by definition, you might be missing the early warning signal, because then you would think that your reconstructed network is the real one, while instead we've seen these Z scores growing over time quite significantly. But still, even when crisis approach and the reconstructed network is no longer in agreement with the real one, it seems that it is crucial to have the information about the reconstructed network, because it is precisely the deviation between the real and the reconstructed network that is creating the early warning signal in this particular case. Thank you very much for your attention.